All right, to save some time, I'm going to do like you said that you wanted me to start with B, and I like that idea because if you can do B, you can do A. A isn't any different than what we've been doing. There's nothing unique about Part A. Now, Part B, if like I said, there's something included in B that we haven't seen before, and if I can show B, then you should be able to transfer that information to solve Part A if that was also a problem. It'll save a little bit of time also. So it says here that a stone of mass 1.6 kilograms is attached to one end of a string 2.5 meters long, of breaking strength 500 newtons, and it's whirled in a horizontal circle on a frictionless tabletop. Well, so it's a frictionless tabletop to begin with when you're solving Part A. But then in Part B, it says find the maximum velocity the stone can attain without breaking the string if there is a coefficient of friction between the stone and the table of 0.3. So in Part B, there is friction. So what that means is I actually have two forces that are both helping me change direction because, again, friction opposes motion. The object wants to move in a straight line. So if I do have friction, in addition to the tension, both of those are going to help change the direction. So we're going to have the friction and the tension both in this direction. I don't know which one's bigger, but I'm just drawing two arrows towards the center of the circle. So we're going to have one of them is going to be the tension, and one of them is going to be friction. Now, anytime friction is involved in the problem, and especially when they give you the coefficient of friction, it probably means that we're also going to need the normal force. So in addition to these forces, we're going to write down the forces that are perpendicular to those in the y direction. So there's actually two directions perpendicular to the centripetal direction. Because if I look at my table here as a surface, the centripetal force would be in one direction, the y would be perpendicular like from the ceiling to the floor, and then the tangent would also be a force that would be perpendicular to the centripetal in the plane of my table. So here's the picture. We've got the weight and we've got the normal force. So once you have those, the next thing to do is to write your descriptive equations based on that picture. So I'm giving points based on the picture and based on the descriptive equations. You cannot write this, what I'm writing now, you cannot write a descriptive equation unless you have a picture because it's literally supposed to be describing something. So you have to have the object that you're describing here, which is the free body diagram. So I'm going to get T plus friction because both of them are towards the center of the circle. And now that's either going to equal mv squared over r or mr omega squared. In this problem, since we're looking for maximum velocity, I'm going to solve it as mv squared over r. And if we, let's see, I'll go to here. Move this out of the way for now. If we sum up our forces in the y direction, we have Fn up, we have W down, so minus W, and I know that those two have to equal 0 because if this thing moves at all, it's going to move in the plane of the table, it's not going to be moving up or down. So those are your two equations. So what I want to do here is I do know that Fn equals W and W equals mg. So what I'm going to do is I'm going to replace friction with mu Fn, but instead of mu Fn, I'm going to write it as mu mg. I know what the breaking strength is, so I know that number there. So actually, I'll know everything in the problem except for the v. So my next step, I'm going to have that T plus mu mg, which would be, again, the friction, is going to equal mv squared over r. So when they say breaking strength, if this thing goes too fast, I'm putting too much stress on my string and it will break. Just like even if you were looking at, like if I'm fishing, and if I'm pulling in on a fish too fast, it's possible if I pull in too fast and try and create too much acceleration in the line, the line is going to snap. Well, same thing here. If I'm going too fast, then I'm putting too much stress on the string and it's going to break. It's telling me that the breaking strength of the string is 500 newtons, so I know that. So now all I have to do is just rearrange this equation to solve for V. So my first step would be get rid of fractions. So I'm going to multiply everything by R, and then I'm going to be dividing by M, so I'm going to get RT plus mu mgr, okay, because each of these has to get multiplied by R. So RT plus mu mgr, doesn't matter where the R is, equals, and when I multiply this side by R, the R's cancel out, and I would be left with mv squared. But I only want V, so I'm going to put the V, it's V squared, but I'm going to divide by the M. Whoops. I'm going to divide by the M, and that would equal V over here. That would equal V squared, because of the square here. So I want V, so I'm going to take the square root. So I pretty much did all the algebra in one step. And when you're drawing, one thing that I'm noticing on tests, when you're drawing your square root, if you're drawing it over a fraction, then make sure the square root goes down far enough so it's clearly not just the square root of the top, it's the square root of the whole fraction. So at this point, we just have to plug in our numbers and we'll have the answer. So we'll get V is going to equal the square root of RT plus mu mgr all divided by m. So putting in those numbers, I need to look back at the problem and see what they are. A stone of 1.6 kilograms. So 1.6 kilograms will go right there. And we'll go down there. It's attached to one end of a string of 2.5 meters long. So if the string's 2.5 meters long, that's going to be the radius. So 2.5 meters goes there and there. Of breaking strength, 500 newtons. So 500 newtons is going to go right here. Now, what I'm going to do is I'm going to write, well, I don't have room, so I'll just leave it as Newton. But a Newton is a kilogram meter per second squared. It would help me show that I'm going to get the units that I need in the solution to this. The coefficient of friction in the problem is 0.3. So that's going to go right there. And gravity is 9.8 meters per second squared. And that will give me meters per second for my answer, because a Newton is a kilogram meter per second squared, so the kilogram part would cancel that, and the meter per second squared times meter, so this term is in meters squared per second squared. Over here, the kilograms will cancel out, and I'll get meters squared per second squared. So mathematically, I am going to get the right units that I would expect, and if you solve this, that answer came out to be what? What was it? 28.0 or 28.1. All right, stop it here. So